To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. Today I am going to discuss with you all full wave rectification of current. Now in the previous chapter we started discussing this, and in that I discussed the activity with you all, how we use the 4 diodes, making the rectification bridge. The diodes connected in such a way that it becomes like a rectification bridge, and when you send an alternating current through it, it is converted to direct current. So you remember looking at the observation, and then in the previous chapter I explained what happens in the bridge, how alternating current is corrected to direct current, or how alternating current is converted to direct current. So now I am going to continue with the discussion. Before I start that, just to recall what we discussed before. So we will go back to the slide and just recall what we learned before. So here, now I explained this. Now we did the activity using an alternating current source, and here we had the galvanometer. But to understand what happens, we use batteries and a light emitting diode, that is B. So there what happens in the first circuit, when the positive terminal is here, current flows through X, D1, then to P, bulb, Q, D3, Y, and back to the battery. And in that you can remember both D1 and D3 are forward biased. They allow current to pass through, while D2 and D4 they are reverse biased. They do not allow the current to flow through. That is one way. But in that instance, if you look at the current flow through bulb B, it's from P to Q direction, this direction. The same way, the second instance, here you can see the terminals of the batteries have been changed. This is the negative terminal, this is the positive terminal. Positive terminal to Y, then from here D2, diode D2, then to point P, the bulb, then Q, then through D4, and then back to the batteries through point X. Now in this instance, D2 and D4, the two diodes that are forward biased are D2 and D4. But D1 and D3 are reverse biased. But again, if you look at this, the light emitting diode, the current flow is from PB to Q, PQ direction. So still the LED is forward biased. In both instances, the current flow through the LED is the same. So that means although the direction of the current flow is different in these two situations, the current flow through the LED bulb is the same. So that means the alternating current is converted to direct current. I explained that using the plots also. Alternating current, you have the positive and negative currents, but when it becomes the direct current, the negative curves, the negative current curves also go to the positive side. So therefore we call it the full wave rectification. I'm sure you all can remember that. So then I'll move on to the new slide now. But we need to discuss this one. So now if an alternating voltage is connected to the circuit in place of the battery, the current flows through the bulb in the same direction, that is from P to Q. So what they have done is, now what I explained before, they have combined it together. Now this is the graph for the alternating current. Here instead of current we have voltage. You can remember alternating current, it can be either the current or the voltage that will fluctuate. Since I used the galvanometer, I label the y-axis as current in the previous slides. Both are correct because in an alternating current, both voltage and current, the direction changes. So this is the alternating current. Here you can see the positive cycles are drawn in red color, the negative cycles, the half of the waves that are in the negative direction are drawn in blue color so that it's easy for you all to identify. So, positive and negative current, that is the direction of the current. So, if we supply this alternate current, instead of using batteries like we did in the activity, using a bicycle dynamo or an alternating current source, if we supply the current between points X and Y, what will happen? Look at the red color arrows. That is for these half cycles. From X, they come to D1. You can remember D1, D2, D3, D4. D1, then to point P, then through the LED to Q, then back to D3, then point Y. That is the positive cycles, these cycles. So, they have been represented here also, the positive cycle, positive cycle. But the next instance, when it becomes the negative cycle, the blue color cycles here, you can see, half waves, blue color half waves, starts from point Y. Y, the direction changes now. Y, look at the blue color arrow, it goes here, this is D2, you can remember that. D2, point P, then the LED, point Q, then back here, this is D4 and to point X. So, can you all understand that? Red color half cycle, the half waves, D1 and D3 are forward bias. They allow the current to flow. If it is the blue color half waves, that is the negative half waves, D3 and D4 are the forward biased diodes. They allow the current to flow there. But this part, I'll repeat that. But this part of the circuit, you can see in both instances, both the red arrow and the blue arrow, they pass through P, then through the LED to point Q. The direction of the current flow is the same. So, what happens to the blue color half waves? They also come to the positive direction. So, now the alternating current has been converted to direct current. And the whole wave, the full cycle of the wave has been converted to positive current. That is why we call it full wave rectification. But like I explained to you all, you still can see that the voltage drops to 0. We get the maximum value, but again it drops to 0. So, still there is a bit of fluctuation. You were able to see that with the galvanometer also. The pointer was deflecting in one direction, but still the deflection was changing. It was not a fixed value. It was changing. So, there was a maximum deflection and comes back to 0. Goes to maximum deflection and comes back to 0. So, that is why we have this waveform. So, that is the full wave rectified direct current. This is the alternating current, that is the full wave rectified current. Is that clear? So, here both the circuits that we discussed before have been incorporated. Why? Because it's going to be the alternate current that is going to pass through the rectifier bridge. Then, figure shows the direction of current flow through the diodes in the two half cycles, positive and negative of the input. So, you have to remember that. Two half cycles, that is positive and negative of the input. Since both cycles of the alternating current through the bulb is made to flow in the same direction in the output, this process is known as full wave rectification. So, you can understand that. Both the cycles of the alternating current through the bulb is made to flow in the same direction in the output. It is the same direction in the output. So, that is why we call it as full wave rectification. Is that clear, student? So, we did the activity. You all saw the observation clearly. Then I explained what happened, and this is how the voltage curves changes. So, that is full wave rectification using 4 p-n junction diodes. Why do we use junction diodes? Because you all know junction diodes allow current to flow through them only when they are forward biased. So because of that, they are useful in rectifying current. With that, I'll move on to the next slide. Now here we have an exercise 11.2 given in your textbook. Explain the reasons for your observations on the galvanometer in the two instances in activity 11.2 and show the variations of the current with time graphically for the two cases. So here they want you to draw the two instances, explain it, and also they want you to graphically represent the two cases. Explain the reason for your observations on the galvanometer in the two instances in activity 11.2. Now, if you go back to activity 11.2, that is the full wave rectification activity. That is what we did before. So, there you need to understand why the galvanometer deflects in the same direction. So, if you are to do that, we need to have the circuit. I will start with the diodes. So, this is how the diodes need to be connected. So, here students, you all can see this is the rectification bridge, the 4 diodes. If we label them D1, D1, D2, D3 and D4. Those are the diodes. Now, here we are going to give alternating current. Now, that is going to be alternating current. And here, instead of the diode, we are going to have the galvanometer. So, that's going to be the galvanometer there. We are going to have the galvanometer here, and that's going to be the alternating current source. Then I have to complete the circuit. This has to join with the galvanometer. So, here, now you can see the circuit is complete. When we provide the alternating current, what will happen? Now, I will use two different colors, pink color for the cycle going this way. Now, the current flows this way, then through this. I will use the pink color arrows. So, here current will flow through this, then through here D1 will be forward biased, then here point P, then through the galvanometer, then here, and then D3 is forward biased, current will flow back there. That is the positive half cycle. Then if we draw the negative half cycle, how does that flow? The current will flow in this direction, this way. It will come to this point where D2 will be forward biased, but here it's going to be forward biased, and galvanometer, it will flow in this direction and through here also back to this point, but here it will not flow through D3, it will flow through D4 and back to the source. So, if you look at the galvanometer, you can see both arrows are in the same direction. That is why you get the galvanometer deflection in the same direction. Is that clear, student? So there, if we draw the graph for the current, now here see, now explain the reason for your observations on the galvanometer in the two instances in activity 11.2 and show the variations of the current with time graphically for the two cases. So here this is what happens when we say two instances. What they mean is the current flowing in this direction and the current flowing in the negative direction. Positive half cycles and the negative half cycles, or the positive half waves and the negative half waves. In both instances, you can see through the galvanometer, the current flow is in the same direction, the positive direction. So, if we draw the graphs for both these, what we have already done before also, now you can remember on this side, we have the initial one, here we have the output. So, this is the input and that's going to be the output. So, here of course I will write this as voltage. Since it's an alternating current, we can use both voltage and current there. Either way you get the same graph. Voltage with time. Here also we have with time. So what happens there? I use the pink color arrows. These half cycles. So here we get the same half cycle like that. Then the black color arrows, we had the half cycles like that. So in both instances, here these are negative ones, but here they have gone to the positive side. These were already positive, that are here. So this is through, this part is through the galvanometer. Through the galvanometer. Galvanometer. Can you all understand that? Is this clear? You can see how the circuit functions. And this is how you will get the plot. So here, explain the reasons for your observations. Reasons. Observation, there was deflection in the same direction, but the deflection was increasing and coming back to 0. So when we say both instances, current flowing this way and this way. So that is why in the previous slides we used batteries instead of showing it as an alternating current source. And here now we have the galvanometer. So galvanometer, you saw the deflection, how it happens. Now you can understand the graph here. So this is the full wave rectified current. Is that clear, student? So that is an exercise given in your textbook related to the activity. So I am sure you all can explain it here. So as an explanation, if you want to write a note, we can say, we can label this as A and B. So we can say, when the current passes through the rectification bridge, it undergoes full wave rectification. that is 1. But still there is fluctuation in voltage. So those are the observations and we have explained it. I'm sure you all can understand that. Now here you can remember the same circuit two different ways. This is how we did the activity, but when we try to understand it, instead of the alternate current source, we use batteries, and here also instead of the galvanometer, we used LEDs. The same way, the same activity, what if you use LEDs in all these? Instead of D1, D2, D3 and D4 and the galvanometer, if you have LEDs, what will be the observation? That is what we will try to understand in the next slide. Right. So here again I have put the same diagrams, but imagine now here already we have an LED. What if all these were LEDs? Now this is also an LED. Everything is LED. What will happen? So we have 4 LEDs. In this instance, when this is the positive terminal, what are the LEDs that will light up? You can remember D1 will light up, D3 will light up and B will light up. So here the LEDs D1, D3 and B will light. So here we are using all LEDs. LEDs also allow current to flow through them only when they are forward biased. In this instance, D1, D3 and B are all forward biased. But in the second instance, what will happen? Here also, instead of the normal bulbs, if we use LEDs. So here we are using LEDs. Instead of the normal diodes, we are using LEDs. So here, what are the LEDs that are going to be forward biased? This is the positive terminal, so current flows this way. D2 is forward biased. Then here you can see B is forward biased. Then here D4 will be forward biased. So in this instance, the LEDs D2, D4 and B are, or we'll say B will light and they are forward biased. So the same thing, we are trying to understand the rectification process, converting alternate current to direct current. To understand that, we can use the same circuit, the rectifier bridge with 4 diodes connected in the correct appropriate manner, but there instead of the normal PN junction diode, you can use LEDs. So then we will see all the diodes light up. That is also possible. You can see D1 and D3 light up, D2 and D4 light up. Is that clear? So this is what happens. In both instances, this LED bulb will light up. That is forward bias. So from there, you all can understand that it is rectification and it is full wave rectification. Is that clear, students? So with that, I have completed the discussion on rectification. We discussed half wave rectification and full wave rectification. But as you all can remember, In half wave rectification, the negative half waves are not rectified. They are not there, only the positive half waves are there. So there is a gap between the half waves. So we call it the half wave rectification. But in the full wave rectification, negative half waves are also converted to positive half cycles. So because of that, there is a full wave rectification, but still, in both instances, the voltage or the current drops down to 0. You can remember the curve. They touch the x-axis, time axis. That means they drop down to 0. You saw that with the galvanometer also. So that will not be enough, or it is not very efficient to use a full wave rectification where the voltage drops down to 0 if you are using an electrical appliance, an electronic device. So we have to have a way to make that correct. That means we need to have a way of preventing the voltage drop to 0. So that is what we will be discussing as smoothing process. So with that, students, I'll move on to the next slide. So smoothing. Half wave or full wave rectification circuit gives out a current flowing in one direction. That is something you already understood. However, its magnitude, voltage or current varies between 0 and a maximum value. Very important. Now we have understood what half wave and full wave rectification is, but you all remember the magnitude, that is the voltage or current, varies between 0 and a maximum value. Time variations of the voltage outputs from a battery, the half wave rectified output and the full wave rectified output from an alternating current are shown in figure below. For the operation of most electronic devices, a constant voltage similar to that obtained from a battery or a constant direct current is more suitable. So, a constant voltage or a constant direct current is more suitable for the operation of an electronic device. That is what I told you all before. So, if we look at the figures, now one is the output of a battery. Now you can remember all these, students. Output from a battery, then half wave rectification and full wave rectification. I am going to draw all the graphs. So here it can be either voltage or current. Here also it can be voltage or current. And here also voltage or current. And this is going to be the time axis. So how will you have from the battery? From the battery, it is going to be the direct current. Now here, this is direct current. That is DC from a battery. Then half wave rectification. Now here, outputs from a battery, the half wave rectified output. What is a half wave rectified output? Half wave rectified output, it was like that. Only the half cycles are there. Then the full wave rectified output, it was like that. Continuous. So here, half wave rectified. This is full wave rectified. So these are the graphs that you all need to remember, students. These are all, they have to be symmetric. So here it is a line parallel to the x-axis. So you can see voltage, current, they don't fluctuate and come to 0 It does not drop to 0. And it is in the same direction, direct current from a battery. But half wave, here you can see one thing, it touches the 0 and also there is a gap between the voltage or the current. So that is also not enough. When we look at the full wave rectified current, there is no gap, but still you can see these points. Now here, 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 the current or the voltage drops to 0. Then of course, it is not enough to operate an electronic device. So we need a current that is similar to this. So to get that current, to make this not to drop to 0, we carry out a process called smoothing. To do this, we need to use capacitors. You are familiar with capacitors. What is the function of a capacitor? When you supply current to a capacitor, it gets charged. Between the plates of the capacitor, there is charges stored. And when you stop the current flow, the charges get discharged. And because of the discharging, there will be a current flowing through the circuit. So that is what is going to be used in the process of smoothing. We will try to understand that in the next slide. So by connecting a capacitor with a large capacitance in parallel to the output terminals of the rectifier circuit, the variation in rectified voltage can be reduced. This process is known as smoothing. So that is something you all need to understand. The smoothing process. So here by connecting a capacitor with a large capacitance in parallel to the output terminals of the rectifier circuit, the variation in rectified voltage can be reduced, and this process is known as smoothing. Figure shows the output of a half-wave rectified after smoothing it using a capacitor. Rectifier circuit is shown in the figure A and output without the capacitor is shown in figure B, and the figure C shows the output with the capacitor. So here this is the figure A, first one. Now you can see this is the alternating current source. This is the rectifier circuit that we used before also. You can see 230 volt, alternating current 50 hertz. That is the power current supply that we get from the electricity supplier to the household. So 50 hertz is the alternating current. Then you are familiar with this. I have explained it to you all. The step down transformer. The voltage from 230 volt is reduced to 3 volts. You can remember that. Step down transformer, where you reduce the voltage of the current. So from 230 volt we get the 3 volt current. Then here you can see we have one single diode. That means it is a half wave rectification process. Now in addition to that, earlier we only had this part, the resistor, or we had the device, the resistor with the galvanometer to observe the current flow. But here we have the resistor between points L and M, but parallel to that. Now this and these are parallel. Parallel to that we have the capacitor here. Now these two plates denote the capacitor. So they are the ones that are going to get charged, and from there charge will discharge. So what will happen is, when there is alternating current given, it is the potential is reduced, voltage is reduced, then only part of the cycle will flow through the diode. So when there is current flowing through the diode, this capacitor will get charged. Then when there is no current flow, when the negative half cycle is flowing, there will be no current flow through the diode. If it is the time duration for the negative half cycle, there will be no current flow. You can remember that. That is why we get spaces between the curves. So what will happen is the capacitor will discharge. And because of that, the gap will be reduced. I will explain that using a graph. We will have to draw the graph again also, but for now, for you all to understand, so this is how we got the graph, no? Half wave rectification. This is voltage or current, and this side is going to be time. Now the positive half waves are there. When it is the time for the negative half wave, then there is no current flow. So during these two instances, the capacitor will get charged. When there is no current flowing through the capacitor, what will happen is it will discharge. Discharge means the charges that are stored in the capacitor will be released. And those charges also will flow through this circuit. From here, they will flow through that way. So because of that, without the voltage dropping to this point, it will flow like that. So instead of the graph coming down, it will go like this. We will not have these parts. Instead, it will still fluctuate, but it will not come to 0. Now here, of course, students, I have just combined both the graph just to explain it to you all. In the next slide, I will separately draw the graph, then you can understand the difference. So this is how we smooth the rectified current. Smoothing of rectified current. So this is the smoothing of half wave rectified current. We will look at the graphs again in the next slide. So smoothing of a half wave rectified current, that is half wave rectified. B is the output before smoothing and C will be the output after smoothing. So if we draw them separately. If we draw them separately here, this is time, here voltage, here also voltage and time. So if we draw the graph, output before smoothing, it is going to be like that. It comes to 0 and there will be a gap. But output after rectification, what will happen is, it will be a graph like that. So here I will draw broken lines because from this point the voltage comes here. And here also from there voltage goes like that. Why is that? Because of the capacitor. So up to here it is the current flowing, but when the current flow stops from here onwards, it is the capacitor that is going to discharge. So from here also it's the capacitor that is going to discharge. So here now you can see it does not touch the x-axis. There is still fluctuation, but the graph does not go and become 0. Voltage does not drop to 0. So that is the process of smoothing. To make this even more efficient, what we can do is we can use capacitors with higher capacitance value. Then there will be more discharge and the graph will be almost like a straight line. It will be more better. So this is before smoothing, this is after smoothing. Is that clear, students? So this is with the smoothing of a half wave rectified. But you can do that with the full wave rectified also. We will try to understand that in the next slide. When the voltage supplied by the diode gradually increases from 0, the capacitor gets charged. This is what I explained to you all. the explanation what I gave to you all have to understand that. So here, when the voltage supplied by the diode gradually increases from 0, the capacitor gets charged. And when the voltage drops back after reaching a maximum value, the charge stored in the capacitor is released. Therefore, despite the voltage supplied through the diode being 0, the voltage across the capacitor does not drop down to 0, although a small reduction takes place. In addition, because the current across the diode is always in one direction only, the discharge current of the capacitor does not flow through the diode. The time variation of the smooth output voltage is shown in figure C. That is what we saw in the previous one. So here you have to remember, students, because the current across the diode is always in one direction. So here, if I go back to the previous slide, in this one, when charges are discharged, charge cannot flow this way, no? So current can only flow in this direction. So when capacitor discharges, the charges will flow through this, not through the diode. That is what is explained there. You have to remember that. So here you can see, in addition, because the current across the diode is always in one direction only, the discharge current does not flow through the diode. Discharge current of the capacitor does not flow through the diode. The time variation of the smooth output voltage is shown in figure C. That is the figure that I drew before. Is that clear, students? So this is smoothing of half wave rectifier. Now we will try to understand smoothing of full wave rectifier. The output from full wave rectification too can be smoothed in the same manner. Figure shows the circuit diagram and the time variation of the output voltage for such a rectification. So now here again you can see. We have the alternating current 230 volt AC 50 Hertz. You have the step down transformer here. Then you can see the rectification bridge there, the 4 diodes, and then here you have the normal resistor, which will be the device or the galvanometer. We had the galvanometer and the rheostat that is going to be connected between these 2 points. Then you can see the capacitor is parallelly connected to this. This is parallel to the resistor. So what will happen? Always current flows in this direction. So when current flows through this, current flows through the resistor in one direction. At the same time, the capacitor gets charged. But when the voltage drops to 0, the capacitor discharges the current. So then what will happen? The current will get smoothed. So if we try to look at the graph here also, you will see the graph. It's going to be like this. Now say we had graph with broken lines so that we can connect it and understand it easily. It's going to be like that, the full wave rectification. Now if you remember, I'll use a different color. Initially, it is the current flowing through the diode in one direction. Up to there, that will happen. But when the voltage is trying to drop, what will happen? The capacitor will discharge. So then, when the graph comes to up to here, capacitor will discharge. Again, the diode will allow the current to flow. When the voltage drops, again the capacitor will discharge. Then you will get a current like that. So now can you see? It doesn't go down. And the fluctuation is also very much less. So then it is a better current, better for the device. So this is the smoothing of full wave rectifier. Is that clear? So in this graph also, this is the voltage and that is the time axis. Now if I draw the axis more longer, that is the time axis. Is that clear, student? So this is what happens in a smoothing process. But in the next slide also, I will draw the two separate graphs one more time. Smoothing of a full wave rectification output before smoothing, that is without capacitor, and after smoothing, we will look at the two graphs. So there I explained it with the same graph. That is going to be time, voltage, time. So here, this is the full wave rectified without smoothing. So here you can see the voltage drops to 0. Now to understand the other one, again I'll use broken lines to draw the plot. So then we can connect it easily. You can understand it. So now, if we try to understand what happens there, initially the current flowing, then the capacitor discharging like that. So there we will get a more smooth current. So this is the plot without capacitor. This is the plot with the capacitor. That is after smoothing. So students, I have drawn these graphs again and again so that you all become familiar with the graphs. You should know to draw these graphs also. Direct current, alternating current after half wave rectification, alternating current to full wave rectified current, then half wave rectified current after smoothing, full wave rectified current after smoothing. You should be familiar with all the different types of graphs. So I'm sure you all can understand the smoothing process also. So these are the two plots. Here the current is even smoother than in half wave rectification. So here you can see here the current is even more smoother than the half wave rectification. Capacitors with large capacitances such as 1000 microfarad, 2000 microfarad are used for smoothing. Smoothing becomes better with increasing capacitance. You have to remember that also. Smoothing becomes better with increasing capacitance. So that is the process of rectification and smoothing. I started the explanation from the previous chapters where we discussed the half wave rectification, then the full wave rectification, and now I have explained the smoothing process also to you all. I'm sure you can understand this process and also the use of diodes. How one diode helps in the half wave rectification and how 4 diodes connected in a rectifier bridge helps in full wave rectification. And then using the capacitors to smooth the rectified current. Now, if you all know the devices that we use in our household, most of the electronic devices, where the mobile phones, the laptops, even the television, most of these, they need direct current. But the power supply that we get to our household, that is alternating current. So, in all these devices, there are power packs or the chargers that are used. They all contain this particular rectification bridge. The transformer and the rectification bridge is included in a power pack. So you have to keep that in mind, students. So with that, students, I am going to end this chapter, and in the next chapter we will be discussing 2 other types of diodes.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.